he's trying to establish a human baseline.
Okay.
And he did this by going and very diligently going and working through the test set. He also went and created a nice user interface online to this data set. So if you want to go and test how well you do, you can go and sit in front of your computer for many hours and go and work through the data set as well.
And so he constructed an answer set based on his interpretation
No,
of
so
images.
there's a baseline answer set. Which is what the network is getting classified as well. So there might be mistakes in it, but both the human and the network get penalized for the mistakes.
Okay.
So the original data set, ImageNet, has been a collaboration between a bunch of people. It's done by Faith Lee's lab at Stanford, but it's got support from a bunch of companies and so on. And what they do is they go and, as I understand it, I haven't looked at it really closely, but they go and they do Google image searches and similar things for a particular class of image, and then they go and they use Amazon Mechanical Turk to go and have the images reclassified by a human to verify that they're in the correct class, and then they go and admit it into the data set if they have that. So they have, many. If I have data here, I have a web browser. Let me go and actually tell you how many examples there are. But they. That's weird. Sorry. Well, maybe that won't be happening. Yeah, I don't know what to make of that. Okay. So ImageNet, those many millions of images in tens of thousands of categories, and there's sort of a subset that people get tested on every year. So the big baseline for object recognition and also object localizations and things like this is an annual contest that gets run, I think, in November, where they go and they have a secret set of questions that nobody sees, and then lots of people go and submit questions, and they have a more public data set that people can go and train on and so on.
So the 95%,
yes.
Is that like a standard deviation of human answers? Because at some point a human had to come up with the answer that is 100% correct, and then the other humans were 95% correct according to that.
Yes. So yes, it's 90. Andre McCarthy was 95% accurate relative to the human answer. So there's going to be mislabeled data. That's just something
on either side.
Mislabeled data is when the data set is wrong.
Right.
And that's something that happens in ImageNet. It also happens in MNIST even. So MNIST was constructed by going and asking lots of high school students and lots of bureaucrats to go and fill out forms with particular numbers.
Right.
And there's lots of things where, that's supposed to be a 2. I wouldn't know that it was a 2.
Right.
My network doesn't either.
Right.
Yeah.
Now my second question was the networks that you build at the end.
Actually, just one last question.
Go.
So on the 95% accuracy, there's also, in addition to there being questions that are mislabeled, there's lots of questions that are ambiguous. So there was the question earlier that I showed you where there was both a Dalmatian and grapes in the image. And so there's a question of what is the thing that you're supposed to be answering, which is why we do top 5 instead of a single top guess, to give an opportunity to recognize multiple things in the image instead of just one. So sorry, go ahead.
So the second question is, how reversible are the neural networks? Because it seemed like the operations you showed at the high level were relatively reversible transformations. Is it possible that you could be like, I kind of want a picture that's 65% Dalmatian, 10% cat, and have it spit out some sort of blurry image?
So the answer to that is a little bit complicated. So first of all,
I imagine it would be.
you can sort of force neural networks when you're working in low numbers of dimensions and you work in a consistent number of dimensions to go and be reversible. So my low-dimensional neural networks typically are, and that's really useful because I can make pretty animations sort of showing what they're doing.
Sure.
Neural networks in general are not bijections.
Okay.
It's unfortunate. And even if they were, there would be a challenge of running them in reverse. Now, what you can do is you can use an optimization process to go and explore the space. So you can go and you can take derivatives of the input with respect to the output you want, and so you can go and tweak something to go and move in a particular direction.
Right, so you can build an image iteratively until it gets roughly the percentages you want.
Sure, or you can also go and you can try to go and find, ask what causes a particular neuron in the model to go and fire, and what was important. Or you could just go and try to figure out what components of an image were important to it being classified in a particular way by seeing how the derivative sense the derivatives. You could get nonsensical images. So one problem is that you can go off the data manifold, and you can get nonsensical images that sort of cause an optical illusion for the neural network.
Right.
So you can get And even images that to humans look like they should still be a car. So there was a paper recently, Intriguing Properties of Neural Networks, that was published last year, or maybe in 2013. And it got a lot of attention because there's a section called adversarial counterexamples, where they go and they use this technique to go and try to find the minimal change they can do to an image to convince the neural network that the image is an ostrich. So that you can take just about it, well, for all the images they took, they were able to go and find images that were barely perceptible to a human, or maybe not even perceptible at all.
That's different.
And yeah, but it goes in the neural network is 100% confidence in oscillation. So, it seems like some of what's going on is it adds really high frequency noise that goes through your edge detectors or things like this. But
right.
Your vision doesn't get fooled by it.
Okay, so human image recognition is context sensitive.
Sure.
And like, for example, if I'm trying to decipher some particularly bad handwriting, I'll basically come up with a theory about what each letter is by looking at various words, and then that will give me enough information to decode something that I couldn't read initially.
Absolutely.
And I just wondered, does that affect your story in any way?
So lots of models account sort of deal with that sort of problem.
Yeah.
So one example is that we have, if you're doing sort of a place where this is really common, is you're working on voice recognition. Of course, so you hear me say hello, and there's a bunch of phonemes there, and I get a probability distribution over what phenome I'm saying at a particular point in time. So I'm probably saying, well, I don't actually know about voice recognition. I've never worked on it, but I'm probably saying in each here. Maybe let's just say that I'm predicting characters. So probably saying in each at the beginning. Maybe I'm saying an E or an A in the next step. Then probably an L and so on. And what people do is they'll go and they'll do other things on top of that. It's called a structured output problem. And they'll do things like they'll go and have a Markov chain. So just look at trying to go and have probabilities of everything modeled by the previous set of characters or the previous few characters. And then they can go and, even though it could have been an E or an A, I know that hello was much more common than hallow. And so I could go and infer that should be an E. Or different probabilistic models on top of that. There's work being done to have neural networks sort of incorporate this sort of thing so that you don't have to have something else on top of it. There was recently a new model called a bidirectional recurrent neural network that tries to go and solve this, but whatever. So structured output problems like that, which I think is sort of what you're getting at, have that sort of that flavor of you can approach it by having another model on top, or you can try to have the model become strong enough that it is able to go and exploit the sort of it gets the context somehow from something else, or different things like this.
Okay.
I guess another example actually would be, Facebook they have a paper about going and using deep neural networks to classify faces, but presumably they don't go and try and classify, and if you're using Facebook, it can go and look at an image and recognize the faces in the image, but presumably they don't go and try and classify the image into every single user of Facebook. They probably go and they go and they look at your friends, or they give more confidence to people who have a higher social proximity to you or whatever. So because they have some sort of probability distribution over how likely it is that somebody's going to be in your image.
Now we need a paper about the minimal change you need to make to Facebook photos to make Facebook decide that your friend is an ostrich.
There you go.
We don't just need a paper, we need a program to do it.
You go through and make everyone's friends ostriches.
So I just had a question about. My question is, do I understand what you were saying correctly? So at the end there, you were saying that.
Right, yeah.
So you have some data that represents a character, this sort of some kind of four-dimensional space.
Yeah.
And then you were saying you can take the set of. Well, you can have all these different transformations you can do to your space, right? Like you were sort of sharing it to help untangle those things. And then you're saying that you can take another space that is the set of all compositions of such transformations you can do.
So maybe this would be helpful.
So like, is that the way to think about it? Like I can take some space and then I can have this whole set of possible transformations I can do on that space, and then I can have a chain of any random combination of those, and you just navigate through that space of operators by finding some minimal. Minimizing the distance or some sort of.
So here, this is I guess a fairly straightforward example, and the chain is predefined. I only have two steps in the chain. I go and I do the first transformation and then the second transformation, and so that there's no ambiguity about what transformations are being done. I have these two transformations, but this chain of two functions that goes together, and now in typical neural networks, you have nowadays for vision, the projection paper used 8 layers. The more recent going deeper with convolutions, one from Google used like 30. So you have these really long chains of functions, and each step they go and they actually branch a little bit and then come back together as well. But it's a consistent chain. Yeah. Now there's more recent work where the way the structure of the network actually changes in response to the input. So for example, when you're doing a sentence, when you just fold over the sentence, the length of the sentence determines the architecture of the network on the one side, and then the answer gets determined by how long it thinks it should. The architecture on the other side is controlled by how long it thinks it needs to go.
So how do you decide what transformation to do? Like if you're showing an example, so when you took the two spirals, like how many is that just one transformation that share the space in that particular way?
I think that's 3 or 4 transformations. But they're applied in a consistent pattern now. So that's just a simple neural network where there's a chain of functions that are composed together, and we just go through the same composition each time.
But if you reversed through those transformations, you might get nonsensical.
Yeah, no, it would be nonsensical. So the thing is that we learn the network. So in that case, those transformations were learned to just be applied one after the other, right?
Yeah.
So we just had them applied in a consistent pattern. Every single example network was ever trained on, it got F1 got done first, then F2, then F3, then F4, then F5. And so applying them in some other way is just completely nonsensical. The types won't line up. The model it was never trained to do that. There's no reason for that to work.
So I guess my question then is, how do you know what set of transformations you should choose? How do you decide this?
So the thing is that the transformations are learned to be composed in a particular way. So when we go and fold over the sentence, let me go and give you a concrete version of a model to talk about.
It's also maybe because I know nothing about neural networks.
No, this is a talk for people who know nothing about neural networks. So if I'm doing my job right, that shouldn't matter.
It's the same kind of thing with statistical networks and stuff. You can choose how you're going to get the answer.
Yeah. I guess I'm more curious about this an algebra space of possible transformations that you could.
Yeah, so let me just give us some concrete examples.
This is not dissimilar from the problem they had in physics, where they had a phase space, and then well, actually it's kind of but they did the same thing. They said, rather than trying to classify the time evolution of some state, you just have each dimension a potential value.
So I'm going to give a slightly different example first. This is what we call a convolutional neural network. And so in a convolutional neural network, this is the sort of one of the key ingredients to running an state-of-the-art results on computer vision. And what we do is we have what we call these modules. This is a non-standard derivation of convolutional neural networks. That is a nice one thing to go through. We have a particular small neural net, A, that goes and takes a small window as input. So it looks at a small section of the image. And it gets applied to every window on the image. And so maybe it goes and detects an edge or a particular contrast in colors or things like this. It does something local. And it gets applied everywhere. And then we have another layer with another small neural network B, and it goes and looks at other sections as well. And so we have this pyramid of A's and B's and many other things, and eventually we try to classify using those. But the nice thing is that we have this local structure. So, and we were able to do that because A is a small neural network that learned to go and operate on any section of the image, and then B is a small one that looked at any, because it wasn't ready to look at any window of A's and so on. So this is a more complicated rule for how to go and compose things. You can think of it as a stencil operation. There's at least one Haskell library that goes and calls it this. But we have this function that gets applied in lots of different places.
So it would not make sense to reverse A and B, for example.
Sure. And now, more recently, so here's the tree structure network again. And so now there's a module that gets, there's another one for each word that goes and translates into a vector, and then another one that all it learned is just how to go and combine two small subphrases into another phrase. And so it gets applied over and over again recursively to go and build us up to a vector representing the entire sentence or the entire review. And another example here, we This is a translation model that matched the state of the art recently for translation. And all they do is they go and they actually reverse the input sentence. So it goes and it goes through a bunch of words, and it goes and it takes a word at a time and then combines it with its previous interpretation of the sentence or its previous representation of previous words and gobbles it up. And then it doesn't unfold, it reaches an end of sentence and stops, and doesn't unfold where it goes and creates things until it decides that it's the end of sentence here and stops. And so here, we have this chunk of neural network, which we call a module, and it gets applied in a particular way, and it learned its structure, it learns the transformation it does in order to be able to be applied in this way.
So do you have an example of the one where the neural network depended on the previous output? A nice pretty example, or?
I mean, well, sorry, not on the previous output, but this one, the neural network structure depends on the length of the input. What's the length of the sentence or decides how many E's there are.
Yes.
Another example here is this one. The tree structure depends on the parse tree of the sentence. So if you put a different sentence, it'll be organized in a completely different way. And we have consistent chunks, consistent thing for going and binding these together. But the structure of the tree that gets combined together varies depending on.
So you've got your A's and your B's, and each of those is a particular operation with some parameters. Is that roughly
so
the case?
A is a particular operation with, it has some parameters that it learned, and B is a different operation. But
Right.
all of the A's are the same operation, and all of the B's are the same
Right,
operation.
and that structure is defined, and the learning part is A and B negotiating which parameters work best
To go
over
and solve the
time.
problem as a whole. Yeah.
Right, okay.
And in practice, there's a whole bunch of layers, and there's a bunch of other things that we throw in, but that's the general idea. Cool. And so this general idea of going and using the same chunk of neural network in multiple places is called wait time. And it's kind of useful because you could imagine, now instead of having to learn, 10,000 neurons, I have to learn 10 or something because I've gone and copied the same ones all over the
Right.
place. And so just like you're prone, if you don't go and abstract and create a function, if you go and write, you're implement your function every time you go and you use it, you're prone to make bugs. The neural network also, if it has to go and implement something, has to every time, it's more prone to make bugs. This
Right.
is sort of a way for a neural network to go and do abstraction in some sense.
Right.
Post office, maybe I'll want packages, so I wasn't sure if anyone can read my writing. If you have some neural network that can read letters, and then you have a neural network that can take letters and then their relational position and form sentences on top, or is that?
Well, so I'll give you one example of sort of a composition between networks, because I think that's a really interesting thing as well. So instead of this one, let me go right to the beginning, and one of the first things I showed you was this. So here, it's two very different neural networks composed together. The first one is a convolutional neural network, which is what I was just showing you with these chunks, things in the same places, so over and over again. And the second one is a recurrent neural network, which doesn't unfold to go and produce a sentence. So you can think of this as just trying to translate images into sentences or something else. I think how Oriole and so forth were talking about it when they were doing it. And so we have these two very different neural networks that are composed together to go and do a task. The job of one is to understand an image or to try and recognize what's in the image, and then the other one is to then go and turn that into an English sentence. One thing I will show you. Talking of my dog, can you figure this out?
This first thing you go
This is
to
gonna work. No, it's over here. Now, okay.
Typing becomes possible.
Yeah, typing is useful. So, convolutional neural networks, for instance, I have a post that Wolf posts on convolutional neural networks. One is on a generalization using group theory, but here's one, and you can see it goes through, and we build up the idea of convnet and max pooling and all this sort of stuff, and different gradations of it, and build an algorithm and stuff like this. So, there's a bunch of posts that just go through the basic ideas about neural networks, and if you're interested. Cool.
Thank you very much.